Hi, we'll move on to section 6.2. So first, the setup is that we have a density function, and the density is a vector. I mean, the parameter can be a vector. So p-dimensional vector. Then this one is a p-dimensional p times 1, and this one is actually p times p. So matrix. Okay. So recall that we have a log density, then scope function is just this, right? And then we are interested, if you are interested in the curvature, so how the change, how this changes, how fast the slope changes is actually gives information about a curvature. So that is called Fisher information. So the Fisher information of, and also if we have n observations, so this is defined for single observation. The scope function and Fisher information are defined for single observation. But if you have n observation, it's very simple, just additive, right? So we have a so this one becomes a summation of the single observation based information. Okay, so if they are IID, then they are all equal, so that n times I, something like that. Okay. Now, this is important property of the scope function. So the first one is that the scope function has zero expectation. Secondly, so what is this is vector, right? So variance covariance matrix. So this one is a S theta prime transpose minus but this is 0, right? The second one term is 0. So basically we want to show this one is equal to this. Okay, so to prove the first one, this one is what? So this is the scope function times density. So that means you now want to times fx. So then means you have a cancellation. And so under some conditions, right? Under some conditions, we can exchange the order. Under some conditions, we can exchange the order of integration and differentiation, which is calculus, right? Pretty advanced calculus. So we don't care. So this one is 1, so that is 0. So that gives the proof for the first property. Second property is now we just look at the okay, S. Okay, well, the idea is, oh sorry, so the idea is you already have this identity, right? Because this one is just this one. So we know that this is 0. So now we are going to apply the differentiation. Okay. So why not just write it as a s, right? S zeta times fx zeta dx. So by the way, we can write it, depends on how you write it. You can write it this way, because we are talking about integration, and then s is actually has of x inside. Anyway, this one is 0 already. So now we're gonna compute the applied. So then how to do that? We use chain rule, right? So this is because it's of two functions. A function. So we have one part, first part, and second part. The second part is this. Okay. Okay. So, and then notice that this guy can be written as times fx zeta divided by so, and then this one is score zeta, zeta x transpose. So if we simplify, the first one is expectation of and the second part is expectation of transpose equal to 0. So which proves this one, because the definition of this guy is expectation of minus transpose S zeta, right? That is the definition. So that proves the result. Okay, so the maximum likely estimate of zeta is obtained by solving the square equation, right? And so how to solve this equation? You can see that, well, so this is your you can, so this is one way to do that is if you do Taylor expansion. So this one is assuming that this one, okay. The second one is close to 0 plus oops, sorry about that. T plus 1 minus T. Okay, so then that will leads to this, right? Because you just it's basically a linearization, Newton method, and then the problem, sometimes the problem is that this may not be invertible. So for a certain value, so better way is to take the conditional expectation of this guy, of the partial derivative, then it is Fisher information. So then this one is called the Fisher scoring method.